Hey, what is up everyone? I hope all of you are doing great. In today's question we have a massless axle has one end attached to the wheel, a uniform disk of mass m and radius r. So this axle is connected to a wheel of radius r and mass m with the other end pivoted on the ground. Okay, the wheel rolls on the ground without slipping with the axle inclined at an angle theta. Okay, the point of contact on the ground traces out a circle with frequency. This should be angular frequency of capital omega. So this question looks familiar. I think JE 2016, I guess. Yeah. Show that omega, which is the total angular velocity of the whole body, points horizontally to the left. Okay, to the left at the instant shown. Okay, fine. We need to also find out the normal force between the ground and the wheel. So this force. Okay, so let us get to the solution. So this kind of question we have discussed earlier from the Pathfinder series. I will mention the video in the description. So there are two kind of angular velocities. One is spin angular velocity, which is due to the rotation of the body along its principal axis, and one is the orbital angular velocity because of the rotation of the whole body with respect to the vertical axis, right? So that one is capital omega. So the spin angular velocity and this orbital angular velocity together will form the resultant angular velocity, which should be directed towards the left and it should be horizontal because this line or this axis is the instantaneous axis of rotation, because this contact point is at instantaneous rest, right? And this point is also at instantaneous rest. So connecting these two lines, these two points, this should be our direction of the actual angular velocity. So omega s cos theta will give you omega, and omega s sin theta will just cancel out the capital omega. So comparing or using these two equation, we can find out the resultant angular velocity, that is capital omega divided by tan theta, and it should be directed towards left. First question solved. Let us come to the next one. So this one is a little bit trickier, and for solving or to find out the normal force applied on the disk due to the ground, we'll use angular momentum concept. Okay, now you can see that there will be, with respect to O, if I want to find out the angular momentum of this whole rigid body, the rule is first we need to find out the angular momentum with respect to the center of mass or with respect to the principal axis passing through the center of mass, and then of the center of mass, right? So with respect to O, this angular momentum of the center of mass would be L2, and of with respect to the center of mass, that means the axis passing through the center of mass, it should be L1. So the total angular momentum should be a vector sum of L1 and L2, right? L1 is I1 omega 1, okay, I1 omega 1, and L2 is I2 omega 2. So the moment of inertia of this disk with respect to this axis, we need parallel axis theorem, that should be ml square by 4 plus ml square. I have considered this length as L. Okay, anyways, so first let us find out I1 omega 1. Okay, that is L1 cos theta. So I1 is mr square by 2. This rod is massless, so it doesn't contribute to the moment of inertia. Omega 1, this one is resultant omega. Omega 1 is omega cos theta. Okay, and there will be another cos theta here. L2, that is I2 omega 2, it should be mr square by 4 plus ml square using parallel axis theorem. Omega 2 is sine component of this omega, simple. So, and another sine theta is this one. So this one is the angular momentum in the direction, in the horizontal direction. So why I am interested in the angular momentum in the horizontal direction? Because this vector is actually changing its direction. Of course the magnitude remains same. This vector is actually rotating with respect to the vertical axis with an angular velocity of capital omega, and the vertical component of the angular momentum does not change at all, neither in the direction nor its magnitude. Nothing is changing, but this vector is changing its direction continuously. So of course this angular momentum is changing, that means of course there is a torque involved here. So first we will find out the rate of change of this angular momentum, okay, because if you push the motion continuously, this Lx vector will keep on rotating. Okay, now for a rotating vector we need to know that rotating with respect to vertical axis, for a rotating vector, suppose there is a vector A which is rotating with an angular velocity omega. Now rate of change of this vector should be equal to the angular velocity cross product with the vector itself. Derivation you can find out in any standard textbook, I won't explain it in this video. So the torque, right, the torque is time rate of change of Lx, which is equal to capital omega times Lx, because sine 90 degree, it is 90 degree, right, and the direction is okay, the direction is dot, that is omega cross A. So here it is Lx, here it is omega, so omega cross Lx will point coming out of the plane of paper, right, so I have marked it as dot. Okay, so now we need to compare it with the torque that is actually created by the gravitational force and the normal force. So with respect to point O, the clockwise torque is due to mg and the anticlockwise torque is due to n. Of course the anticlockwise torque will be more because the resultant is dot. So with respect to O, anticlockwise torque due to n is n times this perpendicular length, which is L by cos theta, minus the clockwise one, that is mg times L cos theta. Simple. Now just compare this with this one, you get this one. Initially we have already got the value of Lx in the form of omega, small omega. We'll just use the value of small omega that we have got, that is capital omega divided by tan theta. Using all these values, put it here, find out n. I won't do the hard work because I have already done that one. Now by solving it, you will get your required result. Okay, so I think here the final result is not that important, but the concepts that have been used while solving these questions are more useful, right, because I think you already have faced this question earlier, and similar type of questions were already solved in the Pathfinder series, and there are similar kind of question in Irodov 2. Okay, so I hope you all have found this video helpful and informative, and do let me know what kind of videos do you want, and I'll see you in the next one. Peace.